And so, since now we have understood what is the difference between electrode potential and the final DTP, and we have defined how the final DTP is the difference between the reductions potentials of one electrode and the other one, it's important to understand how higher the potential difference, obviously higher exactly the difference, higher the final output. And this is the reasons for which lithium-ion battery is so interesting, since we have a very, very small electrode potentials concerning the anode, so the lithium in particular, the similar reactions due to the lithium reduction. So now what is important is to describe why an electrolyte is able to drive charge and close the circuit. What does it mean? So, in general, we know that each single type of electrodes have their own, according to a certain semi-reaction, specific potential. And when we are following the pathway of the electrons toward a higher potential value, we need to understand that we have an increase, for instance, or a changing in the potential moving inside the cell every time we have a change in the composition. And so we have a change in the potential where we are passing from the electrode to the first zone of the electrolyte, the second zone of the electrolyte, a little bit more distance, and so on and so on. But actually, the only type of potential that we can appreciate from an experimental, practical point of view, the only potential difference, if this is the pathway of the potential versus the distance, we can only measure the potential difference between one electrode and the other one, the final DTP. So basically, what does it mean, this plot? That we have here, for instance, the potential of one electrode, the negative one, so the anode. So why the negative? Because it's the electrode characterized with the smaller potential energy, with respect the positive one, that is the electrode characterized with the higher potential energy. It's important don't make confusion about anode and cathode, because the negative electrode is the anode during a spontaneous process, but is the cathode during an electrolytic cell. This is important because the negative and the positive pole still remain always the same during charging and even during discharging, during recharging and discharging, the negative pole still remain the same. But what is actually changing is the description of that electrode. So if in a galvanic cell, during a discharging process, we have that the negative pole is the electrode where actually the oxidation is occurring, so is an anode, during the recharging, the negative pole is still remain the negative pole. That electrode is always the negative pole, but is acting as a cathode, because we are promoting the opposite reaction. It's the same concept we have described in the first lesson. So here what we are actually doing is define why, even if we have a change in the potential every time we are moving away from one electrode trying to reach the other one, we are only able to measure the final difference between the two electrodes. Because if this is our electrode with a certain, for instance, potential, we have even a certain charge acquisition mechanisms. We will see this later, but we have that is charging negatively, for instance. And we have a clip here. This is a clip in order to measure the potential. So we are clipping the electrode, and we have a voltmeter because we want to measure the potential difference, and we have another one. If we want to try to clip the electrolyte, maybe a solution or even a solid, obviously this is not possible, because in the same point what we are doing is creating a new interface, and the clip itself is acting as a new electrode. And so what does it mean? First, that we can only, and this is always true, measure a potential difference. What does it mean? But if we can only measure a potential difference, how we can measure a single electrode potential? That is not a potential difference, is just a thermodynamic measure about the tendency of one species, one semi-reactions to proceed toward oxidations or to proceed toward reduction. So it's something that allows us to understand what it will be the behavior of a species if coupled with another one, and what it will be the pathway of the electrons. So basically, how it's possible to measure a potential that is not a potential difference if we are only able, from a practical point of view, to measure a potential difference? Well, we can only do this with a smart solution exploiting the use of a reference electrode. But before saying this, what is important here is that we can only measure a potential difference, and this potential difference, it will be the difference between the two electrodes. And so the final DDP of the cell, even if we have a changing in the potentials profile as a function of the distance. So the potential, for instance, we can say the potential, we can define this also with this letter maybe, is a function of the distance. But obviously we can only measure the final difference. So this type of sketch is interesting also for another way, because it allows us to understand in which way an electrolyte is able to close the circuit. An electrolyte is a liquid or a solid that can move and drive charge in order to close the circuit. And moving this charge can close the circuit due to the creation of an electrical double layer. What does it mean? We have that the electrical double layer are the creation of, due to a movement of charge of something like this. Obviously we have, this is a mistake. It's a mistake since if we have a negative polarized electrode here, the second one, a clip or a real other electrode, it should be positively charged. So, because obviously we cannot, it's impossible to have the followings of electrode in these directions or and at the same time in the other. So if this is negatively charged, this is positive. And this is important since the overall electroneutrality of the system, it should be maintained. Here we are. So basically what is happening is that in the moment in which we are introducing two electrodes, and we have here a negative polarizations maybe, and here a positive one, so we have on the surface of these electrodes a negative excess of charge, and due to, for instance, the movement of electrons in this direction. This it could be a cathode, for instance, the electrode that is acting as a cathode, and in this case obviously we are creating a defect in the electrode since an oxidation is proceeding, and maybe here we are creating an excess of positive charge, so that is basically a lack of negative charge, a lack of electrons. And what is happening is that since the electroneutrality of the system should be maintained, obviously we have no any type of excess, and for each positive charge created here, we have a corresponding negative charge here. But at the same time, what is happening is that the charge species present on the electrolytes are moving in order to compensate this excess. Here, with an excess of negative charge trying to compensate the positive, and here an excess of positive try to compensate the negative. In order to create something that is close to a capacitor. And what is important now is that we have a different types of model in order to describe this situation. We have the more simple Helmholtz model, in which actually basically we are imagining that all compensations is localized in a single zone directly binded to the surface of the electron, and so the electric field is completely localized in that region, exactly as a plate capacitor. But we know that in general these types of descriptions it's quite not precise, and for the reason year over year new models have been developed, passing from the Chapman, and extremely interesting also for formulation science in order to describe the stability of this Bohr system in the DLVO theory maybe. And in general, basically in this case we are, for instance, considering also the thermal motions of the molecules, even if there are a certain number of assumptions, and the generations of a diffuse layer. So in general, in the Chapman models, or even better in the Stern and in the Graham model, we have that the compensation is not occurring completely in a single zone with an extremely localized electric field, but we have that this charge try to compensate this excess, but in a well-precise range, as I have designed here, in a well-precise zone and not completely localized here. So we have a diffuse distributions of charge, having an always higher concentration when we are approaching the electrode surface. But obviously I want to describe all this model in a dedicated lesson, dedicated about the electrics double layer. And so how the electrics double layers are crucial in order to understand the working principles of an electrolyte in order to close the circuit.